formed by the data link layer. And we will now jump into each and every service or function and see their algorithms and protocols and the theories behind it. And but at very first level, the first thing what the data link layer does is framing. Okay, so yesterday we discussed a little bit about the framing in the last class, but just to reiterate, framing basically why it is required, because if a receiver is receiving a stream of bits like 0 1 1 0 1 0 1 1 1 0 1 1, then in that case how it will come to know that where a particular, you can say, frame is starting. So you need to know some which typically kind of provide in like verbal English. We put some kind of silence in between the two words, and this is how the other person can detect. So sometimes, like if somebody says that somebody is talking too fast, then you say that I'm not able to understand. The precise reason behind that is you are not able to is locate the start of the word and the end of the word, and that is the reason that you are not able to understand. So locating that, synchronizing at the word boundary is word boundary, or you can say the frame boundary, is very much important. So how to achieve that? Okay, that's the problem. So the first possible approach is keep link idle between two frames, and this is precisely is used in Ethernet also. But actually there are certain issues that why we in general don't use this technique. Okay, so first reason is that some encodings in the physical layer. So probably you have not seen physical layer, but as I discussed in the last class, that when you encode signals, you probably encode it like zero, okay, one, 1 0 0 1 0 1, and then let's say zero, and then one, okay, and then one again, and probably this is zero. So if you want to encode 0 1 0 1 0 1 1, then in place of zero, this is called bipolar encoding. There are almost hundreds of encoding techniques. So then you take 0 volt for the for zero, and 5%, let's say this is 5 volt level. Okay, 5 volt or 3 volt, some higher voltage, to put it on the wire. And then basically even the wireless is even more complicated, because there you directly don't use the electrical signals. There you use electromagnetic signals through the antennas. So there it is even more complicated that how actually you encode. But just to simplify the situation, you are encoding it in a 0 volt and 5 volt, and sometimes you really don't know, because if it is zero is being encoded as value, then if the channel is idle, then also you will receive 0 volt, correct? So how do you know that something has started, some bit stream has started, or it's basically an idle? So probably you would be receiving 0 0 0 0 1 1 1. Now is this the message is 0 1 1 1, and this is idle portion, or this whole is 0 0 0, and this is the message only? You really don't know. Okay, so it basically we want to keep the Mac layer completely, you can say, independent of the physical layer. It should not depend upon the physical layer properties, that what kind of encoding technique the physical layer is using to decide that how the framing will work. So that's why the idle, keeping the link idle, does not work sometimes. The another reason is that basically some layers really don't, some physical layers are designed in a way that in order to keep the receiver and transmitter synchronized all the time. See, the synchronization is also one of the biggest issue in communication. Anybody is having any idea about let's say RS-232 communication, serial communication? Have you come across this somewhere in your computer architecture or somewhere? RS-232 serial communication? No?
No, sir.
Okay, so the major problem is the clock between the two devices. Okay, so for example, let's say you are I said that you are transmitting this 0 1 0 1 0 1 1 0, correct? Now you see that we have, let's say this is 1 Mbps design. In that case, each segment is kind of each you can say bit, the duration of each bit is how much? One. Duration of each bit is how much? Please speak. I'm not seeing the chats as of now. Please speak. 1 microsecond, correct? If you have 1 Mbps design, then the duration of one bit is 1 microsecond. Is this correct?
Yes, sir.
Yeah. So in that case, that means both the transmitter and now let's say the receiver is running its own clock. When the receiver is running its own clock, that receiver clock may be faster. So if the receiver is clock is faster, then probably let's say instead of 1 second, it is little bit faster. Then what will happen, by the time the first this, let's say this is the start, so when the first bit is ending, actually it is thinking that it has ended little bit before, and that actually is skew will keep on increasing. So it may happen at some time that actually it is, so once the shift has become more than, you can say, 1 bit duration. So I can explain this in a better way in this manner, like this is the speed of one clock and this is the speed of another clock. Technically, if this is the, you can say, the real time clock. Okay, that means how this is the ideal clock. Okay, the real time clock, one is slower and second is faster. Now after this much of time, at this time they will be actually shifted by this much of duration. This is like faster clock and slower clock. And just to tell you that these clocks are being designed using crystals, and in this world no two crystals can be made identical. So usually the clock, you can say, the clock frequency between any two devices, what you get is at most 20 ppm or maybe 40 ppm for poor devices. Okay, now what, the 40 ppm, that means parts per million. So in that case, like if you are saying that there are two devices, so in 1 second, okay, in 1 second they can differ 40 microseconds. Now if you are working on 1 microsecond bit level, after 1 second they will be thinking some different time, so they will lose the synchronization. So synchronization is very important, you can say, aspect of any communication, that the nodes should be synchronized either in terms of their clock timings to see that okay, this is the start or something, this is where the signal is starting at least. Okay, and then there are some dummy, you can say, bit patterns are sent to allow other side to be basically be in sync with the sender. Okay, so some physical layers, just to avoid any, see, they just keep on sending a special pattern, just to avoid any to keep the synchronization between the sender and the receiver. Now if that is the case, you can't really use the this this idle technique. Okay, if you can't use that, then what is the alternative approach that we can use? So the idea is that you use a special character or bit sequence. If it is a character oriented protocol, that means previously uh, the computer used to understand only ASCII. Okay, so it's like only ABCD and then ASCII characters. But nowadays, most of the systems precisely understand the, you can say, the they basically they really don't differentiate between the image, audio, and everything. Everything is bit sequence, fine, and even the executable files. So you can use some special characters, okay, or some special bit sequences to define the start and stop of the frames. For example, this kind of technique is used in military communication when, especially in simplex protocols, correct? So when somebody is saying something, and then at the end, the soldier will say over and out, okay, then the other person will start. So you really need some kind of markers to special characters. So if you receive that special character, probably this is the start of that. So start of some kind of segments, so that the receiver can precisely locate that, okay, at this point this is starting, and then this point it is ending. Okay. Now, another technique, basic along with that, could be used is like byte counting. So for example, what I can do, I can put a kind of marker, okay, a special character, and then I have data, and then maybe I can say, okay, this is maybe M1 is the start of the data, and M2 is the start end of the data, and then this is one way. Another way, what I can do is I can say that, okay, M1 is there, and this is the byte. So is there start count, and then I say that, okay, 10 bytes, and then I put the data. So then I don't have to, in that case, put the value of M2. Okay, so that I don't have to put the marker M2, because I already know that once the data is started, it is going to be 10 byte, and after that it will end. So that is just the frame. Okay. So that this two simple approaches you can use. Now, for byte oriented protocols, actually there are many, means nowadays these protocols has no significance, let me tell you. But there was a time that we when these protocols were used very heavily. So for all byte oriented protocols, that means wherever two devices actually communicate at byte level, at character level, that means at the ASCII level. So everything for them was actually byte level communication. So there are different protocols like binary synchronous communication, DDCMP, digital data communication message, and point-to-point protocol. So in different scenarios. Our purpose is not really to understand these protocols completely. They are there. This is much more than that. This is our purpose is only to see that how what is the technique that they use for the framing purpose. Okay. So we are not going to understand these protocols. They involve all sorts of data link layer capabilities. But here, only with the perspective that we will just see one slide, that, okay, how these protocols framed their bit sequences. Okay. So, like in bisync frame format, they initially had two sync special characters called sync. Now you might be wondering that, see, what do you mean by special characters? So it's like in ASCII you can always have 0 to 31. You can give it for the special characters and say that, okay, these are the control characters and all. So and that is why if you see that the printable characters starts later. Okay. So you can have these two. They used it two characters because this is basically for the case when the sender and receiver are slow, or maybe their clocks are not synchronized. So when as soon as the receiver sees the sync character, and then it basically starts and basically takes some time to get it synchronized and reaches here. So we assume that, okay, by this time the clock synchronization would have been completed. Once that is there, then it say that, okay, start of header is there. So because every packet has header, so now they have some, you can say, starting of the header also. So you say that start of the header, and then you read the header, and as soon as you receive the start of the text, that means body, that means header has ended. It could be possible because based on the header information you want to do some kind of processing and all. So you need really the boundary that whether header is ended. Now another option could be that after SOH you could just put a variable value here, that is the header length. Then but because here you are anyhow going to start the new body, so the start of text actually is working as an end of header, so that's not a problem. Then you basically have a body, that is the payload or data, and then you have end of transmission, and at the end you have something called CRC, which is called cyclic redundancy check, which basically is responsible for error detections. So the different mechanisms used. The whole idea is to use some kind of sentinel character basically before and after the bit sequence where you want to make the frame boundaries. That's all. So, for example, the triple P format, they use a special character called flag. Okay, means they did not say that. So this is not ASCII oriented. So whatever flag you want to decide, whatever ASCII character you want to decide for flag. And in DDCMP, you have again two sync characters to synchronize the clocks initially, and then you have a which class of this packet is. This packet could be a control packet and all those things, type of packet. The count says that okay, how many bytes are they're going to be in this body, and then you have a fixed size header. So there are different encoding techniques for any frame. Our purpose is just to see the framing here. Okay, now, so in basically similar to the byte oriented protocol, you also have bit oriented protocol. So in bit oriented protocol is HDLC, means in our times this used to be taught very heavily, the high level data link control protocol. But nowadays, because it is not used, this is another, you can say, data link layer control protocol, which was used heavily. But we just want to see its frame. So it's a bit oriented protocol. That means it communicates between the transmitter and sender at the bit level. They just understand that I'm just transmitting, just like you can say the TCP streams, but at the link layer what we are talking about. And then it has also some beginning sequence and ending sequence. These are the special kind of sequences. Okay, we will we will abstract it out, this particular uh, slide and this slide, and we will see these concepts now. But just to tell you that in bit oriented protocol, you use to frame, you use special type of sequences, like you can say 0 1 1 1 0 or something, and then you say that okay, these are your markers, if that is the beginning and that is the ending. Okay, so the whole uh, problem is, it looks very simple, but what if the sentinel character itself, etx, whatever, or ending sequence appears in the body? So for example, if I am transmitting, let's say, ABC, I can do as start of frame stx ABC, and then end of transmission. This is what I can send. But what about when you have a message, let's say, called ABETX itself, because you can't stop the message to have those special characters also, ABETX C. How I will encode this? Because if I encode it like this, STX ABETX CETX, what will happen? What will happen? Anybody, please respond.
Sir, only half of the message is sent then. I mean,
So the message,
uh,
the receiver will basically mistakenly understand that okay, this is the message, correct? That
yes, yes, sir,
STX
yes.
ABETX, that's all. So that is the problem. And then what is the solution? That solution you know from your programming languages. So what is the solution? In programming language, you use this solution, especially in C.
Escape characters.
Escape character, very good. So wherever there's a special, let's say, you know that if you want to put an string which itself is having quotations, correct? Because you put the string in quotations, but if the string itself has quotations, what to do, correct? So these kind of situations, like, you can have an escape character. So what we say that, let replace the every occurrence of these special characters using the escape character. So the script character, I will say A, B, and data link escape. Okay. This is the escape character I will use. Data link escape, ETX, C, and then ETX. Now at the receiver side, whenever the person will receive the DLE and ETX, it will basically remove the DLE, and then so ETX is escaped by the DLE, and this is how you can solve this problem. But What about the message is this: A B D L E C. Then what? If this is the message, what will be the encoding?
There will have to be another DLE.
So it will be A. Okay, the pen. What happened this to this pen? 1 second. Okay, so it will be A B DLE and C. Okay, I start and STX and ETX. But what about if my message is A B DLE ETX C? This is my message. Then what will be the encoding?
A B D
DLE,
L E.
DLE, DLE, DX.
So it will be A B DLE 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 ETX. Correct. So every this will be followed by one this thing. So for example, if I receive at the receiver stx a b dle 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 c etx, is this correct?
No.
No. Correct. Why?
Every odd DLE works as a escape one, and the third DLE doesn't have anything ahead to escape, like it's a normal character.
Yes. So so now you understood that this is how to escape these things. Okay. Okay. So it won't take much time for you to prove it that in any situation there won't be any ambiguity. Okay. However, there are some tricky situations when at the last you have edx and etx that you can do it on your own. Then comes basically bit stuffing. Means in case of bit oriented protocol, you can have an special sequence like HDLC does. Is like they selected that okay, 0 6 time ones and 0. So any message will be preceded and followed by this particular special flag to do the framing. And the trick is that sender inserts 0 after 5 consecuting ones. So whenever in the input or in the data you see 5 consecutive ones, and if you see here in the sequence we have 6 consecutive ones. Okay, so don't get confused. In the this pattern contains 6 consecutive ones. So but the design is that whenever you see 5 consecutive ones, okay, you add 1 0 after that. Okay, and receiver, what receiver has to do, receiver whenever it sees 5 ones, okay, whenever there is a 0 followed by 5 ones, and that certainly will be there, because if there are 5 ones I would have included as 0, so there will always be 1 0 after every 5 consecutive ones. And then you remove that 0. this basically this basically avoids any situation that in your input in between this can come. Okay, now my one question, one thing what we can say, that why not the design was like 6 zeros and 1s? So because until unless you don't see this pattern, because for example, let's say message is this 0 0 0 1 2 3 4 5 and then 0 and 0. Does this contain this flag pattern?
No, sir.
Will still we insert 1 0 after 5 consecutive zeros?
Yes, sir.
Yeah, so that is the only means Tricky part is that even if sometimes the message is already has no problem, you are inserting the zero, but that's okay, because whenever the receiver will see this newly inserted zero after 5, it will anyhow remove it. But this actually making our life easier to basically protect any kind of situation where the 0 6 zeros can 6 1 can come. Now let's say if I would have gone for 6 consecutive zeros, and then what could go wrong? So whenever you see 6 consecutive zeros, then you basically put a new zero. But in
Six
that case, if it,
consecutive ones or zeros.
yeah, I'm sorry, 6 consecutive ones and then 1 0 you
Oh,
put it.
okay.
Correct. So as soon as if you see 6 consecutive ones, you put 1 0. But that is not solving your problem, because in that case, this flag pattern will be still present inside the transmitted message, isn't it? So again, you really, if you really want to convince yourself that in all situations, whatever permutation combination you see, and then maybe you can try to prove it, that means why this is basically going to avoid all sorts of situations where this particular bit pattern, if it is present in the message, okay, then the receiver, then the transmitted message will not have this pattern, and in all cases the receiver will be able to you can say, detect the correct message without any ambiguity. Okay, so now this is just the framing, not much in this. Now we just saw that data link layer services and the framing techniques, bit and bit oriented protocols, how the Sentinel approach is used. Okay. If you have any question in this, then I can take it. Otherwise, I will go to the next topic, which is called error control. Any question? No. Okay. So let's go with this error detection. I mean, in general, we call it error control. Error control encompasses two things: error detection as well as error correction. Because ultimately, you have to first detect whether something is in error, and then only you whether you want to go for the correction. There are different ways of correcting the error, but at the end of the day, you have to, if it is required, you have to correct it. Okay, now first of all, what causes errors? In the last class, I discussed it like distortion of signals due to frequency dependent attenuation. See, how many of you have seen if you're, let's say, if some electrical appliances is running, or like some tube light, or sometimes something is running in your, then your radio or some other device is uh, you can say the voice is getting breaking, or it is distorting that signal. Have you come across any such situation in your life?
Yes, sir. When you bring a
Yeah.
mobile near radio, maybe.
Okay. So actually, this was very prominent in our time when the radio used to be not frequency modulation. They were this FM amplitude modulation, and medium wave signals were there. So it's like there were Vivid Bharti used to come, and if let's say if some scooter, that use a Bajaj scooter, is going from the road, and then you are listening your this thing, your radio inside your room, then you start getting a lot of noise in your radio. Okay, and the reason was that because these scooters have spark plugs, and those spark plugs generate the frequency, the electromagnetic signal in all the ranges, means every range. They work kind of a jammer for other signals. Okay, and then this signal will get so these kind of signals we consider as a noise for our signal. Any signal which is legitimate, because different frequency signals are from different band. For example, the mobile works in 900 megahertz. Now if tomorrow if I get one and Wi-Fi works into 4.4 gigahertz. Okay. Now, if you can see that if there are multiple Wi-Fi hotspots running in a single room, and if everybody is actually using 2.4 gigahertz channel, then the performance of your Wi-Fi will certainly go down. Correct? If you can basically try to do this experiment on your own. In one room, run 5 different Wi-Fi hotspots using your mobile. You will find that the performance will go for performance per hotspot will really drastically go down. However, it may not happen because your Wi-Fi's are very intelligent while selecting the channels. So what happens? There are 20 different frequency channels. So when a Wi-Fi starts, it basically scans all the frequency channels, and wherever the interference is minimum, it basically starts using it. Okay. So because of that design and all, it is able to. But once you have more, you have limited number of channels, and then it has to basically take some channel anyhow. You can't do much. So then the performance goes down. So any kind of outside signal which I really I can't interpret and understand is noise for me. And you can have different kind of noises present in the system. Even you know that if a current carrying wire generates electromagnetic signal, isn't it? So in that case, if some wire line is going with high voltage wire line is going nearby your mobile or something, that is also emitting the electromagnetic signals, which unfortunately will fall. Some of those part of that will fall into the frequency range which you are using for the communication, and then they will interfere with the primary signal. Okay. So this is the major cause of this thing. And second major cause is like attenuation. Correct? Attenuation is like you all understand that when you transmit a signal, electromagnetic signal, its energy gets you can say it's inversely proportional to the distance it covers, and not only inversely, it's basically the square of that, 1 by d square. So the intensity after 2 meters, whatever it is, after 4 meters, it will be actually 1 by 4. Okay. And after 8 meters, it will be almost 1 by, after, yeah, 8 meters, it will be 1 by 9 something. So the energy reduces, and the receiver needs some energy, at least the threshold energy, to basically make sense out, or yeah, to make sense out of the received signal. Otherwise, it basically simply fails. So so that is the reason that why this thing can come. Now, the error could be of two types. One is like random single bit errors or bursty errors. Now, random single bit errors is like if I transmit 0 1 1 1 0 0 1 1 0, then the receiver maybe some bit randomly get flipped from 1 to 0, and then receiver will basically get 0 1 1, and then this bit will be an error, and then 0 0 1 1 0. So like every we assume this kind of error when we this kind of error model, where we say that every bit has some probability of being in error. Okay. So that is one situation. But in practice, usually this doesn't, it is not like that. In practice, if there is some error source, noise source, that is going to be there for some time. For example, if this is your signal, if let's say this is your signal. Okay. See, anyhow, the signal is encoded in bits, but ultimately your signal, once it is modulated on the channel, it will be something like this. Okay. You don't really know this. There is, for receiver, this is a signal. And then suddenly a spike comes from some external source. So this spike is going to destroy this much of portion of the signal, whatever is decoded, and then accordingly it will basically that those bits will be interpreted wrongly. Correct? So now, depending upon the basically the width of this spike, okay, that means interference, and the 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 channel rate, okay, or the data rate what you are using. Let's say if you are using 1 mbps, then your bit length is 1 microsecond. If it is 1 microsecond, and if the 1 microsecond pulse comes, then it is going to destroy only one bit. And we can fairly assume that these pulses come randomly at some point. then you can assume this is a random single bit error. But for the same noise signals, which are kind of 1 microsecond duration, but you are working at 100 mbps data transmission, that means your 1 bit is kind of 110 nanosecond. Okay, 1 bit is actually 10 nanosecond. Then one spike is going to destroy nearly continuously almost 100 bits, isn't it? Am I correct? I'm waiting for your answer.
Yes, sir.
Yeah. So this is how the burst error. So a signal could be a single can work as a single bit error for one type of you can say data transmission, or which is working at lower rate. But same signal can work as a bursty error for another type which is working as a higher rate. Okay. So usually handling this bursty error is tricky, and and even modeling, like when you try to model the performance of your protocols and things like that, it is easier to assume random single bit error, so that and if every spike independent of each other, so you can always model it as a uniform distribution, and that helps you to calculate an IID, that is identical and independent random variable, and that helps you to model your error independently, which basically allows you to calculate the packet error rate. But when the burst error are there, it is kind of correlated, and then the modeling becomes a little bit tougher. Okay, so why detect errors? Data fidelity, prevent wastage of. One is, yes, you really want data fidelity, that is, you don't want the incorrect data, and but at the same time, you also want to prevent wastage of resources. So maybe I should put the correct question should be, why detecting error at data link layer? Okay, because probably transport layer, if let's say if it is already doing, then can I basically skip it here? Okay, so the idea here is like, no, because sometimes if error is very high, let me just. Okay, this is coming very. Okay, 1 second. Hmm. No, it's fine. So let's say you are transmitting data from here to here, here to here. This is a multi-hop transmission. Okay. Now, if the packet got lost here itself, and if you are working at the TCP layer, correct? So then you have to basically, this person will also transmit because it won't be detected here, correct? So this person will also transmit, this person will also transmit, and ultimately the receiver will come to know that the packet is in error if you are detecting at TCP, and then the timeout will happen. So see, unnecessary others were transmitting, and then you were eating up these bandwidths. Okay, but if you can detect here itself, then you can simply drop packet here itself. Means I'm not talking about that whether you can ask for the retransmission at the link layer, but only detecting at the link layer, you are actually saving the bandwidth of further links by avoiding by dropping the packet here itself, so that those bandwidths, those link bandwidths are not wasted, correct? So why to unnecessary transmit when you already know that this is actually, this packet is in error? Okay, so it also saves your resource. So two reasons: one is, yeah, you really want the correct this thing, but at the same time you want to save the bandwidth. Okay, so then what to do? What to do? You know you have errors, you want to detect it. One is basically what to do after detection. So what you can do, you just drop the frame and let the higher layer TCP will recover losses. So let's say if it got at the first hop, the timeout will eventually occur at the TCP. Okay, that is one approach. You don't do anything. and sometimes few losses really don't hurt applications. For example, in case of audio, if you see right now also what we are talking, okay, means our ears are so intelligent that even if one word or one word or one character of a particular word is lost, we will be able to make it out. Okay, make it out means error correction. So that is like for audio, it's you really don't need the complete reliability. But think about a doc file. Is it okay that that if I send a message that I will, okay, I will ship the material tomorrow, okay, let's say this is the message, and instead of that ship p, this becomes t. You can think about what will happen, correct? So you really don't, you are not okay with when you are transmitting a message or a file and then say okay, one character gets changed. No, that's not correct. Okay, so recover, basically then you have two options. You recover frame, and recover frame means like you perform some kind of error correction techniques. So that means the frame itself carries some redundant information, so that even if it is in error, you can somehow recover the correct message. However, always remember that that will happen with certain probability. If you want the packet to be recovered with 100% probability, that means one probability one, then you need to put infinite amount of messages, infinite amount of redundant message. But this is a probabilistic word, and this is means whatever remaining probability, then the TCP will take care of it, no problem. So that is the correction has always some probability, and even the detection always has some probability. So property, the probability. Second is that okay, you just detect it, you drop it, and let the retransmission at link layer itself take care of it. Okay, so receiver signal sender on error, or maybe you can also send the negative acts, basically saying that see one way to drop it, send the negative act, NAC, and then this thing you drop it, don't say anything, timeout at the transmitter at the link layer will go off, and then it will retransmit. Okay, so these are the things what you can do. Okay, so let's discuss that what is the difference between error correction and retransmission. When you should use what means, should you use correction, or you should just ask the transmitter to retransmit? Means the correction still now you have not seen, but you have already seen stop and wait, go back and all those retransmit things. Now, first thing is that the correction always requires more redundant bits than the detection that we are going to see, but this is the thumb rule. Okay. If you want to correct it, you need to put more number of bits than if you just want to detect it. So that means if you can think of that, if the error rate is very less, let me if let's say if for 10 bits you are putting up 10 additional bits, so you are putting up 20 bits, and if that say error less is very less or negligible, then in, in 1 Mbps, if you have 1 Mbps data, 50% information, so the effective throughput what you are only getting is 5 Mbps, correct? That's not good, because you are all the time just transmitting the packet in the anticipation that if it will be in error, the receiver can recover it. Okay, here in that case retransmission is good, because whenever there is a packet drop, and the packet is detected in error at the receiver, then only the retransmission will happen. On the other hand, reverse, if the packet error rate is higher, okay, then you are unnecessarily retransmitting all the time, and even it is increasing the delay. But so if your requirement is delay stringent, like you can't afford the retransmission, and that is going to hamper the performance of your system, then it is better to have the error correction, correct? And at the same time, error correction is also good when the link delay is very high, like in case of satellite communication. So So that is basically a trade-off, and the real systems actually to be used. So in your receiver, there is a kind of you see even nowadays people are using machine learning at the physical layer and data link layer also to all the time predict and detect that okay how much erroneous the channel is going to be in future. If you can predict it properly, then you can set your mode accordingly. So you can, if the error rate is going to be less, then you switch on to the stop and wait and retransmission mechanisms. If the error rate is higher, then you start putting up the code. Even the codes are very intelligent. Like for example, you can have 1 bit correction capability, 5 bit correction capability, and 10 bits correction capabilities. Okay, that essentially says that if there is 1 bit in error, I will be able to correct. If there is a 5 bit in error, I will be able to correct. Or if there is 10 bit in error, it will be able to correct. But there is a cost associated with it. If you want 5 bit capability, the number of redundant bits that you put in the data will be much higher than the capability when you require 1 bit correction capability. Okay, so it's a kind of trade-off, and basically if you can precisely you can say precisely measure the or anticipate or predict the error probability in the channel. Okay, by monitoring the old drop rate or something, things like that, you can kind of tune the parameter for this corrected error correction capability, and even whether you want to switch back to the stop and wait, that means retransmission mechanisms. Good. So this is what actually happens in the system. So this, yeah, error correction is useful when especially in wireless, because wireless has higher error rate. Okay, and also it is good when you are going for a higher link delay, where especially in case of satellite communication. Okay, so now let's see this overall framework of means, before directly jumping into that exactly the algorithms and protocols, how do we detect errors. Let's see a common framework. Okay, basically this, which we give you the fair idea about all the terminologies which we'll use in future. At the same time, it will give you the theoretical background. So the whole idea behind any error correction and error detection technique is add redundant information to a frame to detect or correct errors. Okay, that is, you add something redundant. For example, it basically it is just a joke that, let's say if you are uh, going to a bus, and then you just bought one, asked for 2 tickets. The conductor said that, see why, actually this joke is from Supandi. So who has basically, who those who read him, they know. So then the conductor says that why you are asking for 2 tickets. So he said that, see, what if because you are only one. So he said that, what if my one is lost, then I will have at least two. So just out of curiosity, the conductor asked that, okay, but what if you get if second one is also lost? And do you know what was his answer? Anybody? What could be the funniest answer in that case? What if the second is also lost? So he said that, then I have pass. Okay, so that is the height of redundancy. But at least that is the same basic we use in error detection and correction. You basically make the things reliable through the redundancy. Okay, so um, am I audible to you people? Because I'm not receiving any kind of response from your side. Okay,
Yes,
fine.
sir. Yes.
Yes, yes. Okay. So basically, in general, a sender adds k bits of redundant data to m bit of message. So technically, when you are sending m bit of message, it becomes m plus k bits. Okay. Now k is usually derived from original message through some algorithm that we will see one algorithm later. but you have some algorithm to derive these k bits, attach these k bits into the data. Now at receivers, receiver will apply the same algorithm on this on M, and see whether whatever this K you have attached, whether it is matching. He also gets the receiver also gets the same K, and if that is the case, then basically this is correct. I mean, with the checksum and everywhere you have seen this, but here we are going to see it very formally from the theory of coding techniques. Okay. Now, just for the example sake, in case of detection, which actually Ethernet uses, the frames are nearly about 12,000 bytes, but K size is only 32 bit. Okay, so it K is very, very, very less than M. Okay, so you are not putting up, so you can still detect. Correction is not in Ethernet, but whenever the correction is done, the correction is done in Wi-Fi. There you use a terminology called code rate. The code rate is like how many the useful masses divided by useful pluses plus the remaining pluses. Then the code rate will become 1/2, and you will be surprised that actually in Wi-Fi this code rate changes from 1/2 to 5/6 depending upon the interference situation. So if you remember, I said that when the Wi-Fi scans and Wi-Fi hotspot is running, at that time itself, it basically makes an kind of estimation of the error and the interference in the environment. According to that, it sets its code rate. Now, if its code rate is 1/2, you can always think that the actual bandwidth you are going to get very less. Correct? So that is what it is. Means there are n number of reasons that why we get different bandwidth. This is not only the reason that why you get different bandwidth. Your server could also be slow wherever you are connecting. Okay, so there are n number of reasons that why some suddenly you get different should stop here, and then in next class we continue this discussion on designing the error detection and error correction. If anybody is having any doubt, you can ask.
So you said that the nodes in between can tell that there is an error and stop, like the wastage of resources.
Okay.
So who tells the to retransmit in that case, and how does it work? Because it's not reaching to the receiver right now. Like you said,
Okay.
negative acknowledgement is
Okay.
sent.
Okay. So very good. Actually, the negative acknowledgement technique really does not work at transport layer, because at transport layer, especially in Ethernet, the link layer drops are negligible. Okay. The reason is that while the packet is not reaching to the receiver is because it kind of dropped in congestion somewhere in router because of less size due correct. So when the total anything correct, you
Yes,
really
sir.
did not. How will you know that it should agree? So those that got the mechanism, however, in Wi-Fi and in link layer, what happens? Most of the time, the packets are in error. That means some of the bits are corrupted. The packet is actually received intact. Means the physical layer is really able to decode a packet if the header, and if you can say the synchronization physical layer headers and some of the data link layer headers are not corrupted, you will receive the packet. And if the packet error is in payload, okay, then only the only problem is that the payload is corrupted. So many times what happens that you received it. Okay, it's not like you did not receive it. You received it, and now one option is now you just keep quiet, drop the packet, wait for the at the transmission end to time out. That's an act based mechanism. But you just to retrigger the early retransmission from the transmitter side, you can send in another a control packet, which we usually call NAC, and say that, okay, just retransmit this because I did not get it correctly.
Got it, sir. Thanks.
Yeah. So can anybody basically just quickly answer that what is the when somebody should use NAC based solution and when an ACT based solution, like just like error detection versus correction, NAC based solutions and ACT based solutions. So maybe you can think offline, and this is yeah interesting topic also. However, we are not going into the detail here, but you just think that, so what are the situations when NAC based solutions are good, then ACT based solutions, and vice versa. Okay, with this I'm just disconnecting. If nobody is having any further question, thank you.